This is the last of the three parts on the intro to vectors from section 6.6. We talked a little bit about all different forms of representing vectors. I ended the last video with the zero vector. This one we're going to pick up with a unit vector. I had mentioned earlier that there is such a thing as a unit vector. A unit vector is a vector that is 1 unit long. What is the unit? Well, it depends what you're measuring in. It could be a foot long, could be an inch long, could be a centimeter long. It's 1 unit of whatever linear measure you have. So we had talked about 2 unit vectors that are common, right? The I unit vector is the one that goes 1 in the x direction, 0 in the y direction. The j unit vector goes nothing in the x direction and 1 in the y direction. But we can create unit vectors that have any angle measure, right? They could be 45 degrees, they could be 22.7 degrees. But the whole point is it's 1 unit long. So if you want to create a unit vector, what you do is you take the vector, you find its magnitude, and you take the vector and divide it by its magnitude. So for example, if you had the vector 3, 4, you would go and you would find its magnitude, and the magnitude of the vector, I happen to know, is 5, right? 3 squared plus 4 squared. Square root of 25 is 5. So then you would take the vector and divide each component by its magnitude, 3/5, 4/5, and you would have a vector that went up and to the right into the first quadrant that was exactly 1 unit long. And you could use the magnitude formula to find out if this really is a unit long, and it is. So let's try one. Okay, we've got 4i minus 3j. Find the unit vector in the same direction that has a magnitude of 1. So the first question is, what is the magnitude of vector v? So the magnitude of vector v is going to be the square root of 4 squared plus 3 squared. Oh, look at this. 4 squared is 16. 3 squared is 9. That gives me the square root of 25, which is 5. So then we apply that formula. We take vector v, we divide it by the magnitude of vector v. So vector v is 4, negative 3. We're going to divide it by the magnitude, which is 5. So we get a new vector that's got a horizontal component of 4/5, a vertical component of negative 3/5. Or we could write it as 4/5 in the I direction minus 3/5 the j direction. All right, the second part of the problem said to verify that it has a magnitude of 1. So to do that, we take the new vector and we apply the magnitude formula. So the magnitude says it's the square root of a squared plus b squared. So it's the square root of 4/5 squared plus negative 3/5 squared. And then we work the order of operations, right? If I square 4/5, I get 16 over 25. If I square 3/5, I get 9 over 25. Now combine them over a common denominator. I get 16 plus 9 over 25. Well, 16 plus 9 is 25. So square root of 25 over 25 is just 1. So that verifies that that vector has a magnitude of 1. It's in the same direction as 4i minus 3j, except now it's got a magnitude of 1. So this is my answer. This is the actual unit vector. And then the second part was just verifying a magnitude of 1. Now, this says suppose I have a vector, and I want to break it down into its components. So if theta is the direction angle from the positive x-axis, you can break it apart by separating it into sine and cosine components. Because remember that when you have a right triangle like this, there's your angle measure. Sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. So the opposite side is over here, the adjacent side is over here, and when we use the AI and BJ notation, A is the horizontal, B is the vertical. So it makes sense that in the I direction, we're going to multiply by cosine because that's the adjacent side. We're going to multiply the J version, or the vertical, by sine because that's the vertical component. So we can separate a vector into its components by multiplying the magnitude of the vector times the cosine of the angle, magnitude of the vector times the sine of the angle, because remember this hypotenuse here is the magnitude of the vector. That's how long it is from the origin to wherever we're going. So let's try this. This is the jet stream. Jet stream is up in the atmosphere, blowing at 60 miles per hour in the direction of north 45 degrees east. Express its velocity as a vector in terms of I and j. So what does this look like? I'll give you a picture in a second. But if I was doing north 45 east, remember this is bearing. We had done this stuff at the end of chapter 4. So that means from the north, I go east 45 degrees. So this is the north. From the north, I go in the east direction 45 degrees. Like that, 45 degrees. It says that it's blowing at 60 miles an hour. So 60 is the magnitude of that vector. Okay, so maybe the vector looks a little bit like this. It's 45 degrees here, and we know this whole thing adds up to 90, so that means that this angle here is also 45 degrees. All right, from that, we can fill in some blanks regarding horizontals and verticals and angle measures. So it tells us that the jet stream is blowing at 60 miles per hour, so 60 is that component over there. How do I separate these things? Well, this component here we'll call A. We could use the formula, or we could write it out in terms of sines and cosines and right triangle trig, right? Cosine is adjacent over hypotenuse, so if the cosine of theta is A over 60, then 60 cosine theta is A, and theta is 45 degrees, so we get 60 times the cosine of 45, which is root 2 over 2, so 30 square root of 2. All right, I'm going to run through this as a formality, but I bet you know what the other one is already. If this is side B, then sine is opposite over hypotenuse, so sine of theta equals opposite over hypotenuse. Multiply both sides by 60, and I get 60 sine theta is B. Well, theta is 45 degrees, and the sine of 45 degrees is also square root of 2 over 2, so I get 30 root 2 for the B component. And so the question says express the velocity in terms of I and j. So the velocity vector is 30 square root of 2 in the I direction, that's the A component, and 30 square root of 2 in the j direction, that's the B component. All right, so I can separate it into two parts. Does that match with the formula I was given here? Sure. Right, the magnitude was 60. The angle was 45, so we did 60 times the cosine of 45 in the x direction. We did 60 times the sine of 45 in the y direction. All right, and there it is worked out. All right, this one is going to be a little bit longer application, but it's good to do one that doesn't involve just whole numbers. This one involves multiple vectors. So it says two forces of magnitude 30 and 60 pounds act on an object. The direction of the first force is north 10 degrees east. So you notice that this force down here from the north has an angle of 10 degrees. Then it says the direction of the second force is north 60 degrees east. So this one comes from the north down 60 degrees. Find the magnitude to the nearest hundredth of a pound, the direction angle to the nearest tenth of a degree of the resultant force. So the resultant force is the one that comes out of the middle. Right? That's my result. The best way, I think, to tackle this problem is to break the two vectors that were given, the two forces, into their components, and then all we have to do is add the components together. Once we get the components of the resultant force, then use right triangle trig to figure out what the angle measure is. So I put this up here in the corner as sort of a reference for us. The first angle here is 10 degrees, right? North 10 degrees east. So what that means for vector force 1 is that if it's 10 degrees from the vertical, it's 80 degrees from the horizontal. And it gives us that's 30 pounds. So I'd like to break this into A and B. Right? How do I do that? Cosine and sine. So cosine of 80 is adjacent over hypotenuse. So that means that the horizontal force is 30 times the cosine of 80 degrees. If I want to find the vertical force, then all I have to do is multiply by sine, right? Because sine of 80 equals b over 30. Hit both sides with 30. 30 times the cosine of 80 is b. All right, for force number 2, that's 60 degrees from the horizontal, from the vertical. So if it's 60 degrees from the vertical, that means it's 30 degrees from the horizontal. All right, for force 2, now that we've got that angle in place, we can draw ourselves a picture and use the same right triangle trig that we did before. The only difference now is that this angle down here we said was 30, but this over here is now 60 pounds because it's a different amount of force. That's A, that's B. A is still cosine, so I get 60 times the cosine of 30 degrees as my A. Cosine 30 degrees, square root of 3 over 2. So I get 60 times square root of 3 over 2. That gives me 30 square root of 3. That's A. For B is going to involve sine. So 60 sine of 30 degrees is A. Sine of 30 is a half, so half of 60 is 30. All right, so let's list our forces up here in decimal form. So for force 1, I've got to get my calculator out and do 30 times the cosine of 80 degrees. 5.209. And then this should be not cosine, this should be sine. And then for the other one, 30 times the sine of 80 gives me 29.54. Okay. Force 2, we said was 30 square root of 3. So since I have the other ones in decimals, I might as well write this in decimal form also. So 30 square root of 3, 51.962. And then the second component is just 30. So now the resultant is the sum of those two forces. So take 5.209 and 51.962. Add them together, I get 57.171. And then for the other one, I can see that 30 plus 29 is 59, so 59.54. Don't know what happened to my third decimal point. 30 sine 80, 29.544, so I'm missing it. Okay, so that's the resultant vector. What was the question I was supposed to answer? Here, let's go back to the question. It says, find the magnitude to the nearest hundredth, direction angle to the nearest tenth of a degree. All right, so the magnitude might get a little bit goofy looking because it's got decimals in it, but it's a pretty easy calculation. So, magnitude of the resultant is going to be the square root of 57.171 squared. So there's the first coordinate squared, 59.544 squared. Add them together, take the square root. You do that, I do that, we'll compare answers. All right, I do it on my calculator. I take the square root. I get 82.547. The question said to the nearest hundredth, and so to the nearest hundredth, this is 82.55 pounds of force. The second question asked me about the angle. And so here I've got 82.55. This is the angle that it makes with the positive x-axis. And what else do I know? Well, I can fill in one of two things, or both really. The resultant is a combination of moving over and up. So if I just have the resultant and a theta that I'm looking for, I don't have enough information to solve the problem. So let's fill in one of the sides here with information we know. How about 59.544 for the vertical distance? I could have used the 57 for the horizontal distance as well, and now I've got enough information to solve the problem. The other thing I can do is fill in this bottom here as 57.171, and then use tangent from the original numbers rather than from the resultant. The advantage of doing it that way is if I messed up the calculations of the resultant, then I can still get the angle measure correct because they're based on the original measures to the resultant. So let's try that. Let's do tangent as opposite over adjacent. And so tangent of theta equals 59.544 over 57.171. And so theta is the inverse tan of that. All right, let's throw it in the calculator to see what we get, and we're done. Right, I get 46.164. So 46.164, the question said to the nearest tenth, so 46.2 degrees. So if I want to box my answers, there's the number of pounds, there's the degrees that go with this resultant force. So if you're pulling on these, or these two forces are acting on this object, then the result is that 82.5 pounds of force are going to be going in a direction 46.2 degrees from the horizontal. So obviously this is a little bit more complicated problem, but nothing terrible, right? We took the two forces and we broke them down into their components. We added the verticals to the verticals, horizontal to the horizontal to get the resultant, used the magnitude formula to find out how much force was being exerted in that direction, and then from there, used inverse tangent to find the angle measure. I think the last slide just has the answer on it. 82.55 pounds, 46.2 degrees from the horizontal. Right? And that's the last of this first section on vectors.